Alexey Kurakin. I'm from Google Brain team. So yeah, as she said, I was here last year and I was talking about one specific attack actually using adversarial examples, and today I'm going to talk about a broader topic of adversarial examples, what's interesting happening in this area and why you can find it useful. So, first of all, well, let's start from the question why adversarial examples are important and what are them at all otherwise. If they're not important, then maybe we shouldn't talk about them. So first of all, what is adversarial example? This picture will demonstrate you very well, but I'll briefly explain. So let's say you have image classifier. Any image classifier, but let's assume that it's very well trained, that it has high accuracy on your test sets, and you use it to classify images and you satisfy with it perfectly. And what's usually happening, you take an image from your test sets, or like just some other image, you feed it to your classifier and you get a label. Like in this case, we get a hamster, image of hamster, we get a hamster. Then, what's happening, let's say some adversary slightly modify this image, added like this gray rectangle with a noise to your image, and got a new image which is almost the same. I bet you cannot notice any difference even from the front row. But then your image classifier like says, this is no longer hamster, this is cauliflower, or something else. Moreover, your image classifier says, I'm 99% confident this is cauliflower. And, well, this is called adversarial example. So this is an image or some other object which fools your classifier. So in this presentation, I mostly talk about image classifiers, but this is also applied to like sounds, text, and other domains. There are some caveats, like text, for example. There's some other related problem, garbage class examples. For you, all these images looks like nonsense. They're just nothing. But they're crafted in a way that image classifier thinks this is something meaningful. Moreover, it thinks it's something meaningful also with 99% confidence. Well, this is related because it's also like a sound way to fool machine learning classifier and make machine learning classifier thinks that there's something which actually not there. I won't focus too much on the garbage class examples, but I just mentioned that most of the techniques which used to adversarial examples applied directly to this problem. So now the question is why adversarial examples are important. First of all, well, again, look carefully at these two images. Actually, if you sit in the front row, you probably can notice, like, for example, like, if you look carefully at this star here, and at this star over here, you might notice there is something going on there. If I wouldn't tell you, you probably won't even pay attention, but yeah, there's some small difference. But the thing is, like, if you're not paying attention, this looks the same to you. But for machine learning system, it's not. And that means that maybe we don't fully understand something, and also our machine learning systems lack robustness. So because small changes of input lead to large change of output. Another thing, well, it's a security event, so we're all interested in security. So, and adversarial examples do pose some security problem. Essentially, the idea is that you can fool computer and human won't even notice that something wrong going on. To illustrate this even more, I'll show you just a few videos of the possible adversarial attacks. So, this one actually presented last year at GeekCon, and the idea is there are two images. One is normal, one is adversarial. So this one, normal image, classified as a library correctly. This one classified as a prism. And this is done through an app which is running on a phone. So I'm perceiving image through a camera and recognizing it. So in this case, like, perturbation is pretty noticeable. You can see that the right image actually has a lot of noise, but at the same time, it's pretty obvious to human that both images are washer. At the same time, this one is a washer and this one is a doormat. So yeah, this was demonstrated last year. I won't go into more details. I'll just show a few more interesting videos. This is a turtle, and it's recognized as a rifle. This is the interesting thing that the authors of this work, they actually made a 3D model of turtle and painted in a certain way, so if you look from different angles, it's still recognized as, well, not a turtle. And one more thing, which is a recent work by Google Brain, this one. So you also using a camera and looking at the table of the coffee mug, you see like classifier recognizing that a coffee mug and espresso on the image, which is correct. Now we put like a patch near this cup, and now classifier thinks that it's a toaster with a very, very high confidence. So the numbers here, like from 0 to 1, is a confidence. Well, now it become banana, but now we move the patch a little bit more, and it's again toaster with almost 100% confidence. So all these 3 videos demonstrate that actually our machine learning classifier could be susceptible to this problem, and you may be able to use this to maybe like attack a machine learning system. Now, let's talk a little bit more about details. How adversarial examples are happening, like what possible attacks you can do with them, and how you do these attacks. So first of all, like the idea of the adversarial example to fool a classifier, and you can fool it in 2 different ways. One, you just make a classifier output a wrong prediction. Well, go back. Yeah. I just go back a few slides. And one, let's say, yeah, I'll just show you this image again. So this image classified as a hamster, and this was classified as a cauliflower. So one goal you might have as an attacker, you want to just make sure that image is misclassified. You don't care how, but you just want to make sure that this is no longer hamster. Another goal is you might have as an attacker, you want to make sure that image classified as a specific class. Let's say if you have like a face recognition system and you want to be recognized as a specific person. And there is actually like some paper published last year attacking specifically face recognition system. Though there are like some drawbacks, but as a proof of concept it's interesting. So this is like one classification of attacks, that we have a like non-targeted attack when you just want to fool a model, and targeted attack when you want to fool it in a very specific way. Additionally, there is a notion of white box and black box attacks. So what does it mean? Let's say you have your machine learning classifier and you train it yourself, you know everything about it. And this is one situation. And if you want to craft a adversarial example for something you know really, really well, maybe it's easy. Another situation, like let's say somebody else gives you a machine learning classifier and you know well very little about it. You maybe know the architecture they use, like if they use like neural networks or something else. Maybe know even like how many layers they use in neural network, but you don't really know like all the parameters of the model. And this is called the black box scenario. And in case of white box, you can imagine maybe you can do like some hardcore math and you can come up with an adversarial example. But for practical purpose, black box case is much more interesting. And the good thing is, well, maybe good, maybe bad, that even in black box case you can attack a model. And how you do this, you use the property of transferability of adversarial examples. So the idea is that, let's say you have one model which somebody gives to you, and you have another model which is you want to attack. Then what you can do, you can craft adversarial examples for the model somebody gives to you, and just try this adversarial example on the other model, and you have a good chance that you will succeed. Well, the actual chance depends on many things, like what data set you use, how exactly you craft adversarial examples, but there's a chance. So for example, if you look at this table, it's contain exactly this chance. So how successful you will be if you use one model to craft an adversarial example and another model to classify them. So this was done on a specific data set called MNIST, which is pretty small and this kind of research data set. But this property still apply on large data sets, and maybe the numbers will be lower. So in particular, what it means here, if you look at the upper left corner, there is a DNN and DNN. That means that we used some DNN. DNN stands for deep neural network, to craft adversarial examples, and then we use some other DNN or deep neural network to classify them. And we, like, in 40% cases, we successfully attack it. So this is like transferability of adversarial examples, and this helps us to craft an attack in a black box case, which is important like for practical purpose. Now another way how you can think of the adversarial examples, you can have a digital attack versus physical attack. Well, digital attack, or maybe code for those who engineers in the audience, code probably tells by itself. You really like take an image, or well, maybe in the case of neural network, a tensor of floating point numbers, and feed it into your machine learning system. And the thing is that in such case, if it's an image, you have a fine-grained control of every pixel, and you can change it by 1, by 2, by 3, or by whatever you want. And this is a digital attack. Now, physical attack, or how we call it physical attack, that's what I showed in the few previous video. You don't really have a fine-grained control of every pixel. Instead, your machine learning classifier perceive image through a camera. And as you know, like camera, first of all, introduce some distortions. Second, it introduces some noise, which is random, and you cannot really model. Maybe you can model distortions, but it's unlikely that you can model noise because it's random. So in this case, the main point is that in this case, you cannot really have fine-grained control on what's going inside the classifier. So, and this is a physical attack. So again, for digital attack, I'll show you a few slides like of the hardcore math, how to craft adversarial examples. For physical attacks, you essentially rely also on property of transferability to make an attack. So you essentially rely on the fact that even if image slightly perturbed, your adversarial example will still remain adversarial. So now, these are like all different dimensions how you can do the attack. It's first of all targeted versus non-targeted, then black box versus white box, and digital versus physical. And now I focus a little bit more about digital white box attack. So yeah, now here's the math. So that is, let's say you have a classifier F, and you want to fool this classifier. What by fool I mean that you just want this to output a label L, which is not a correct label for the image. So your source image is X, and then you try to add some noise R to the image to make it so in a way so the image will fool the classifier. And well, so we can write this mathematically as well, this equation that our neural network on image plus noise equals desired target class. We restrict our images to being 0.1, 0.1 because typically in machine learning we normalize images to be from 0.1. Well, typically like bytes are from 0 to 255, but when we feed them in the classifier, we divide everything by 255 and we get numbers between 0 and 1. Well, this is all fine, but you can say, well, okay, I can just like completely replace the image and it will be classified as something else. So here it comes, the first line essentially tells us that we want the noise to be as small as possible. And this is an optimization problem. There are like techniques to solve it. It's quite slow to solve actually, but it works. And this was one of the first papers about adversarial examples. In later, well, people realized, well, it's too slow. Let's try to do something faster. And here it comes another method, which is actually called fast gradient sign method, well, which implies that it's fast. And here's the idea is very simple. So X is an image, and X adversarial is your adversarial image. And J is a loss function. Essentially, you can think of it, J tells you whether your classifier is right or not. But the main point is that J includes your equation for your classifier. And then like this triangle sign is this gradient. So we compute a gradient of essentially of your neural network, and goes into, and then do a step in the direction of the gradient, and well, it works. It's not perfect. It's like, well, depending on the model, it could have like 40–60% chance of success, but it works. And you can craft a successful attack, and it's very, very fast. It's essentially almost as fast as just like classifying an image. Well, maybe just 2 times slower, because you do forward pass and backward pass, but it's very fast compared to previous method. Yeah, it's fast, but well, it's not as good as previous one. So what we can try to do, we can try to do this repeat iterations of this procedure a few times with smaller step, and then it becomes much better in terms of like success rate. This is like one thing. This is another thing which is very similar, also repeating previous procedure multiple steps. So with this procedure, you can actually achieve like almost 99% success rate of attack. At the same time, it's like roughly 10 to 20 times slower than the like fast sign, which is still pretty fast. And one more thing I just want to mention, another method which is considered one of the strongest attack, one of the strongest white box adversarial attacks, strongest in the sense that you need this very small perturbation to actually cause misclassification when you use this attack. And here's the idea, very simple. You look at this part. This is difference between adversarial image and the source image, and you try to minimize it. And in addition, there is a second term which essentially tells you, I want this to be misclassified. And this is just encoded this way. And with these two terms, you try to minimize the whole construction, and it gives you adversarial examples, which are, well, have very high, well, also like more than 99% success rate of attack. In white box case, it's slower than the fast gradient sign. It's slower than iterative fast gradient sign, but it's much faster than the very, very first slide I showed you, where you like solve some like more general optimization problem. And again, just to reiterate, if you don't know the classifier and you want to do a black box attack, then what you can do, you just train your own classifier on the same data set or a similar data set, craft an adversarial example for your own classifier, and then you hope that it will be also adversarial for the target classifier. And you have well, some chance, depending on the combination of data set classifier, of the success. So now, well, that's all good. We learned how to attack, but the question is like, if we cannot defend, it's kind of hopeless. The good thing that we actually can defend, and as I'll tell you later, in black box case, we can defend relatively well. In white box case, this problem is still not solved, but I'll tell you about a few defenses. Well, one obvious thing which people came up initially, like, as I showed you this adversarial example, the difference is very small and look like a noise. And people were asking, what if we just do denoising, like, or blurring of the image? Will it help? It does help to some extent, yes. If you blur an image, if you like use a white box attack, then on your classifier, then you blur an image, and then you classify it again, then very likely the blurring will destroy your attack. At the same time, the catch is that, let's say your attacker knows that you do blurring or you do denoising, and then attacker exploit this and craft adversarial example, well, taking blurring into account, and then your blurring do nothing. This is the bad part of this defense. So it works as long as attacker doesn't know that you do blurring or another type of like input transformation. Some variation of this called gradient masking. It might be less like obvious, but the idea is that if you look at the formula which I showed you before, there is this operation which is taking a gradient. And your like formula for neural network is hiding in here. And so now, what if you cannot take a gradient of your neural network? You just add some non-differentiable function inside your neural network or any other classifier, and then this formula no longer works. Simply, you cannot take gradient. Well, it just means nothing. And yeah, this was another like defense, proposed defense for against the adversarial examples. It also works like good in a white box setting, but the interesting thing that it completely fails in the black box setting. You just train another classifier which behaves similar to yours, but which is fully differentiable. You attack your fully differentiable classifier and then transfer adversarial examples to this non-differentiable model. So what's more promising actually adversarial training. So as we remember, our neural network misclassified adversarial examples. So what if we just add them to a training set and retrain our model? And essentially this sort of works. And how it works, we just, on each training, so how training works, on each step we just compute the update of the model parameters and apply them. So in case of adversarial training, we take a model weights on each step, we craft adversarial examples for this current state of the model, then we combine them with the clean examples from the data set, and this use combine mini batch to compute updates of the weight. So the important part that you do this on every step and not just craft adversarial example once and like use them as extension of your training set. So yeah, it actually works in white box case pretty well. Well, it depends again on the model, on other things, but yeah, it works in general. The tricky part is that it doesn't work very well against iterative attacks in white box case, and it doesn't work well against black box attacks, and I'll tell you in a second why. As I showed on previous slide, you can, well, one of the failed defenses is gradient masking, and the idea is to add non-differentiable function. So what happened in the adversarial training, in this kind of adversarial training, your network learned that, well, it doesn't really need to become robust adversarial examples. It just needs to learn weights in a way that gradient will be close to 0. And, well, yeah, if your gradient close to 0, you also like, I mean, the procedure will fail. But it doesn't provide real robustness. It's just hard to construct adversarial examples, but not impossible. And to deal with this, well, few people from Stanford and Google actually develop ensemble adversarial training. The idea is that it's very similar to previous one. You have still like orange trainable model for which you craft adversarial examples and add the mini batch. But another important thing that you have a bunch of fixed models which are not altered by training procedure. And these fixed models provide another set of adversarial examples to like extend your training set, and this helps to prevent model to learn how to mask gradients. And as we noticed, well, depending on the attack you use, this actually indeed helps to become robust adversarial examples in both white box and black box case. Again, the caveat is that it better works in black box case, and it doesn't work very well against iterative attacks. Iterative attacks still able to find like problems in your model. At the same time, we noticed that iterative attacks not transferred as well as the like simpler fast gradient sign attack in the black box case. Another thing, so yeah, this is I talk about attacks and defenses, and now I'll tell you one thing. What else we tried to do to kind of solve the problem? Because this is indeed a problem, and well, what we can do, we organized it's Google Brain and the collaboration of Kaggle and the conference which is called NIPS, organize a competition. So the idea of the competition is let's encourage people to develop attacks and defenses. And so for this competition, people can submit 3 things. They can submit a non-targeted attack, which is a program which fools a classifier. Targeted attack, which is a program which fools a classifier but in a targeted way. And a defense, which is actually a classifier which hopefully robust to all attacks. Then we run all of them against each other. In particular, like orange boxes are attacks submitted participants. The blue box is defenses also submitted by participants. Then we provided a data set, which was, well, part of it was secret, part of it was known. And we run this against each other. So the idea is that, yeah, we use data set, we run all attacks, craft adversarial images, then all this like a huge amount of adversarial images we run through all defenses, get classification results, and then knowing how defenses classified our images, we can tell whether the classification score was correct or not. And now, if defense successfully classified image, it gets a 1 point. If not successfully, it gets 0 point. If attack produces an adversarial image which fools the defense, it gets 1 point. If it fools 2 defenses, 2 points, and so on. And same for targeted attacks. For targeted attacks, well, if the classification score was our desired target class. So very easy. If you succeed, you get 1 point. If you fail, you get 0 points. And you sum up all points across all images. And in the end, we can see how well attacks and defenses submitted by participants. So what we noticed actually, the ensemble adversarial training, which I mentioned before, we provided as a baseline, which actually did relatively well, okay. I think it's like showed 80%. I think accuracy on adversarial images around 80%, while on clean images it's supposed to be 100% accuracy, because we pre-selected images, so all images from dataset will be correctly classified by some baseline. So 80% not bad, not perfect, but not bad. And our competitors actually, well, improve on top of it. So yeah, this is ensemble adversarial training. Participants improved the defense, and they actually achieved, well, almost like, well, not 100%, but 95% accuracy on using some form of adversarial training combined with a bunch of other tricks. This is quite interesting, quite inspiring. This means that, well, maybe there is a hope that we can defend. At least we can defend against a black box case, which is the most pressing from the security point of view. Because white box case, you still can argue, well, you usually don't know the model you're trying to attack, or if you know the model, then probably you have access to the system, and then probably like you can attack it in 2 other ways. But black box case, if we can defend against it, then this is like at least some security guarantee. So yeah, that's almost all what I want to tell you. So I'll just briefly remind what I talked today. So first of all, adversarial examples are samples which you feed into a classifier and which could be used to fool your machine learning classifier. There are like different ways of adversarial attacks. It could be white box versus black box. White box, you know everything. Black box, you don't know everything about the classifier. And digital versus physical. Where digital, you feed directly pixels into classifier. Physical, you give an image and the classifier perceive it through a sensor. There are various ways to defend against adversarial examples. A bunch of defenses looks well in case if attacker doesn't know it, all security or obscurity, but don't really work if attacker knows about them or anticipate that they may be used. At the same time, there are like potential defenses which might work, like adversarial training and sub-adversarial training, and it seems like, well, our competition showed that at least it might work in the black box case and provide us some hope that our machine learning models will be completely broken. There's still a lot to do in this area. First of all, it will be interesting to provide robustness in the white box case. And this is an interesting theoretical problem in particular. Another thing, well, even in black box case, well, we have a competition even, and there are good results, but on the defenses. But still, well, maybe if we work harder, we still will be able to break them, so there's still room to improve. And also, we got like 95% accuracy, but not 99, 100, and we want, well, the more the better. And, well, that's all what's happening in adversarial examples world. I hope you find this talk useful, and I have a little bit of time to answer a few questions from the audience.
Hello. Hi, my name is Alvina. I'm from First Republic Bank. I work with a lot of startups, founders, and VCs. So my question goes to your adversarial competition. How long did that take?
How long? So actually, like, we ran competition for 3 months. I mean, we let participants to develop, like, develop attacks and defenses for about 3 months before the final judgment. Is this answer your question?
Yes, thank you.
Any more questions? Okay, I guess then I'm
More
done.
questions, guys? I have so many questions, but that would take all day. Oh, I see a hand over there.
Okay.
Hi, I'm Michael, a reporter with PC Mag, and I was just wondering, can you talk about what sort of attack scenarios you kind of envision with, like, what are the possible weaknesses that we might encounter in the real world, and what sort of defenses you envision?
Well, I guess anything you can imagine where the goal is to fool a classifier. So if your classifier is responsible for like making a decision and you want to alter the decision, you can use the adversarial examples or garbage class examples to do this. So yeah, whatever you imagine. I guess you can pick any area where machine learning is used, and you probably can come up with something, some form of that. Yeah.
Cool. Anyone else? All right, well, thank you so much, Alex. Before you leave, though, we have a special souvenir gift for Alex. If we could bring up Xietao to present that gift. Hello. Hello, Mr. Is it Tao or Xie? Okay. Oh, right.
It's like, I don't know, 16 pounds maybe.
Oh my gosh. Bicep, look at that. Oh my goodness.
You okay?
Yes. That is really heavy. Thank you very much.
Okay, thank you.
Let's give him another round of